Hello and welcome to today's Electronic Design and Power in Motion webinar. Our topic today is Solving Thermal Management Challenges of the Data Center, sponsored by Parker Hannifin. I'm Bob Vavra with Endeavor's Design and Engineering Group. Let's talk about how you can participate in today's presentation. If you have any technical difficulties during our session, simply type your issue into the Ask a Question box, and a member of our team will assist you. You can also click on the question mark Help button in the upper right-hand corner of your screen. We also welcome your questions during our event today, and we'll get to as many of those as we can during the Q&A session that follows our main presentation, so feel free to send in your questions at any time. To do so, simply type your question into the Ask the Question box and click on the Send button. Please be aware that today's session is being recorded and will be available on the Electronic Design and Power in Motion websites within the next week. You'll be notified by email when the archive is available. So let's meet our speakers for today. Timothy Marquis is the new Product Engineering Manager at Parker Hannifin's Quick Coupling Division. He joined Parker in 2001 as a product engineer. He's held various project leadership and engineering management roles and is now the new Product Engineering Manager at the Quick Coupling Division in Minneapolis. He's also worked on various heat transfer projects over the last 15 years and has been focused on data center thermal management for the last 3 years. And Liana Jaskot is the Quick Coupling Product Unit Manager at Parker Hannifin's High Pressure Connector Division in Europe. She joined Parker in 1994 as an R&D product manager, and she's evolved to become a quality manager and then took on strategic pricing functions, is now a product manager for the Quick Coupling business unit. She's got extensive knowledge of thermal management and has been working in the market for more than 15 years. So welcome to both of you. And Liana, why don't you get us started on today's presentation?
Thank you for introduction, Bob. Hello, everybody. So today we propose you the following subjects: short introduction about cooling and the types of cooling, specification insights and system considerations, some application examples, and some Parker solutions. So most of the current data centers use air cooling. Cold air is pushed in to negate the air heated by the computer hardware. So the air is pushed into the cabinet, but due to internal construction, small spaces, the circulation is not perfect and the heat is not removed correctly everywhere. ASHRAE recommends a temperature range between 64 and 81 Fahrenheit for an optimized functioning of the data center. Need to find the right balance to maintain this temperature range and avoid downtime. As the processors become more and more powerful, it is important to remove correctly the heat released all the time in order to avoid risk of failure and high costs that the downtime can generate. In addition, if certain chips get too hot, they will automatically slow down, which will affect the performance of the whole system. Therefore, if you cannot cool well enough, you will limit the performance of the complete system. As computing power and the number of devices goes up, the energy continues to increase exponentially. Data centers already consume 1 to 2% of the global electricity supply. This is only going to increase without any substantial energy efficiency gains. If you're running your data center inefficiently, the cooling budget can be twice the cost of buying and running the hardware. That's a lot of cash wasted on ventilation and air conditioning. Data centers continue to pack more computing power into smaller spaces to accommodate processing intensive applications such artificial intelligence and advanced analytics. Each rack consumes more energy and generates more heat, giving greater importance to cooling systems to ensure safe and efficient operation. Liquid is now one of the best ways to cool down electronics due to the high thermal conductivity of water and sustainability benefits. In addition, it is possible to use the heat for other things like heating buildings or use it for other industrial processes.
Thank you for going over that, Liana. I'll take you through the different kinds of liquid cooling as they are in the industry today. In particular, there's two main types that you'll find out there. There's direct-to-chip, and then there's immersion-style cooling. Both have different advantages and different disadvantages, and obstacles, and they're both offered in both a single phase or a two-phase, meaning the coolant either stays one phase as it goes through and cools the IT gear, or it'll change phase, going from liquid to gas, and taking advantage of that heat of evaporation to be able to increase your efficiencies. So a direct-to-chip liquid cooling, commonly you'll see it as a cold plate or cold plate loops, something along those lines. It really, the heart of it is you're getting the coolant, whether it's a single phase or two phase, like we talked about, directly to that main heat source. It's typically the chip. It's a GPU, it's a CPU, it's any of even the more exotic different types of processing units that are going out there today. And sometimes it'll also be used for other parts of the IT gear, but it doesn't go through everything. It'll usually you're targeting those main heat generators. And the heart of this then is going to be the cooling distribution unit. It's a pumping unit that's going to be circulating the fluid around to the chips and to the different areas where it's required. So that coolant will move from the pumping unit or the cooling distribution unit over to some rack manifolds, and then through those it'll go through each piece of IT gear, where it'll directly interface with the chips through, usually, like I said, a cold plate, and then it would come back through the manifolds and reject that heat to the environment somewhere. Either it's a single phase where it's going to be doing it directly, through a heat exchanger. Maybe it goes to a rear door heat exchanger in an environment where it's doesn't have access to a lot of cooling water that comes in, or it could be tied into a facility cooling water for a major installation. Then that water will come back, and then we'll continue the process. In addition, you can have this as a single phase or a two-phase setup. Single phase, like I said, water is or some sort of water glycol mixture is typically one of the best choices, and that it's got a fairly high heat capacity. You're able to, through not too much delta T temperature rise, you will be able to capture a significant amount of heat that's generated off those GPUs, CPUs. The fluid doesn't change state as it goes across, so it makes it much simpler. It's one type of fluid that's processed all the way through. A two-phase system then is kind of the opposite. Obviously, it's two phases of the same fluid, your refrigerant, like your house, like your car. As it goes across the IT gear, it picks up heat. It takes advantage of that heat of evaporation, which engineering school says it takes a lot more energy to do that than it does just to change a couple degrees of temperature on a solid single phase of fluid. So the advantage then is you're really taking advantage of that efficiency, but now you've got to manage two phases. Obviously, you can't have gas come back into it because then you'll lose all your cooling. You have to make sure it gets from that gas back to a liquid, and then be able to keep keep that pump going and be able to manage those two phases as you go along. So there's a little bit of added complexity there. So in terms of transitioning from air to liquid cooling, it's the directed chip style. Typically, you can add this into an existing data center, and there are a number of things to add liquid cooling with, maybe a rear door heat exchanger, or different ways to reject the heat that you can retrofit, either with the rear door or if there's some sidecars, heat exchangers, different ways to do this in an existing system today. They can be efficient and quiet. They reduce the energy consumption that's necessary out there. And by doing this, you can reduce your geographical barriers. Meaning, when you try to set up a data center in a very warm climate or a tropical climate, you're able to control exactly what you're cooling a lot more efficiently and effectively than maybe you would otherwise, and you make that consistent. Obviously, with the additional parts and trying to get to this additional cooling, you have more technical complexity, more components. Obviously, what everybody is most worried about, I think, with a lot of the liquid cooling is the potential for leaks, which the system design needs to go directly into that to make sure that you set yourself up correctly, so that you don't have some of the failures that you might experience otherwise. And then there's cost. The infrastructure cost is more than it costs to get an air-cooled system. Obviously, as Liana said, the amount of cooling costs that you pay throughout the life of the product makes a total cost of ownership actually significantly less for these liquid-cooled solutions, and in this case for the directed chip. Then the other style, immersion cooling. It's what it sounds like. You literally take a server blade or a piece of IT gear and you submerge it. Obviously, you're not using water. I think we all can say that would be a bad idea. It's going to be some sort of a dielectric coolant. It can be an oil. Sometimes there's the highly fluorinated type of coolants as well. They're out on the market. There's a number of companies out there that we can reference that specialize in those types of somewhat expensive fluids. But this ensures that all the heat is removed, so there's no risk of any kind of external changes in temperature, any external factors that are going on. It really isolates and cools completely the entire piece of IT gear. We're not just talking the CPUs and GPUs anymore. We're talking the RAM and the boards and all the power supplies. Everything is completely submerged, so you end up getting 100% of that heat that you can capture and be able to bring back and use for something else. So it also eliminates the risk of air pollutants, different humidity factors. Also, it eliminates fans. It gets rid of the cost and the power used by the fan, but it gets rid of vibrations. And there's definitely some people who have done some good work showing that will help some of the IT gear in terms of its life and reduction in failures. So, and then there's, like I said, there's no air cooling system. Like you can completely remove the fans, and as you take that heat out, you reject it somewhere else. It could be still close by, or usually in an immersion system, I think you're going to be trying to connect that to maybe a facility water, or something that takes it completely out of the building, so you're not doing some of those retrofits or sidecar heat exchangers. You plan for this in advance. So then, again, single phase and two phase, showing a single phase kind of on the top left is essentially you're circulating fluid through the tank, and then you can actually be able to take that, reject it to outside heat. The two phase, very similar. You're boiling this fluid off of the IT gear directly. Then you have to capture it. It becomes a gas. It becomes something you have to capture, and then you have to condense back down, either inside the tank, or you do it outside. You can capture that and pump that back in. But the big key is that you have to be able to manage that and deal with that. But it does a really good job on the two phase of boiling directly off of those really high heat generating items, like again the CPUs and GPUs. You can see that really boiling on those particular spots to be able to take that energy away very quickly and effectively. But then actually being able to return that back in is the key. Again, it's dielectric oils, different types of coolants, and it's something that you completely submerge the entire unit. There's a few different ways of doing it that would be maybe in rack or in where you can submerge just a piece of the gear. But generally we see this as a large tank where everything is set up horizontally. It does have to be planned for in advance because it's no longer a vertical rack, generally speaking in this case. It is something that takes a little bit more to plan for from the beginning and execute, maybe a horizontal with a way to be able to bring the IT gear up and out of an immersed fluid and then be able to get it clean and dried and be able to service different components of it. So again, if we're trying to transition to an immersion system, I mean, immersion system, it's really highly efficient. It gets rid of the air pollutants, humidity, vibration, fans, super quiet, cools everything, and all that helps a lot. Some of the cons is it's a little bit harder to service, like we just talked about. You have to get the IT gear out, or you have to be able to access stuff that's in it. And it does require you to think about how you lay out your data center differently. And the initial cost can be high. Some of the fluids can be costly, and it's not something you easily go in and retrofit. At least the traditional way of doing this isn't easily to go into an existing data center and retrofit. And some of the fluids, it's depending on how you go about it, just have additional environmental concerns that you have to mitigate and be able to just be prepared for. So if you're looking at these different kinds of systems, so thinking how are we going to go about setting up a data center, either we're retrofitting or setting up a new one, and it's time to do, hey, these GPUs and all this machine learning or AI is causing us to really run a lot of really high performance now, and we really need to look at liquid cooling, or if you just want to go after the environmental efficiencies and the energy efficiency. You just you have to set up which type of system you really want to go after, and you need to look at the different kinds of technical elements, and is it existing or is it new is going to be really key. But then you can look at the different technical elements of a stamp, which is kind of how we specify a lot of products within Parker. Make sure we have leak-free connections. Obviously, mitigating the risks of water in a data center is huge. And making sure any kind of ergonomic concerns, connection forces of different coupling products, and installation is key. And then having the proper fluid flow, pressure drop, having the proper fluid compatibility is huge. And just to make sure that all the thermal engineers are happy that as this flows evenly across all of the IT gear, you can get appropriate cooling everywhere. And then really just making sure you have the right testing and qualification processes. I'd say that's for sure on component levels as well as system levels to make sure that as you get things set up, you're proving it out as you go. So STAMP is key. It stands for size, temperature, application, media, and pressure. And this is really what if you came to Parker, this is the stuff we need to know to help you get the right products within your particular system. We have to make sure that all the products work within your ideal working temperatures. Chemical compatibility, that's huge because if you have a dielectric oil versus a glycol coolant, there's different materials, and you got to make sure you're using the right ones, or you could have some of those data center disasters or leakage that could cause a significant problem within your data center. And then what kind of size is it? What's the pressure? What kind of weight is important? Is everything easy to access is a huge one. That's for the serviceability part. Are you reaching down underneath and trying to get a large connection at the very bottom at kind of an odd angle? If so, then we might have to look at what are the ergonomic concerns there, and how easy can you access all this stuff? And corrosion goes along with the material compatibility as well. Just for all the metals, making sure we don't have galvanic issues, and making sure that as we move forward, the products are going to last the lifetime of the equipment. So ergonomics, like I said, ergonomics is a concern. Making sure, especially when you're doing service on products and you get to some of these larger products, if you get to a large manifold style connection and you end up having to reach underneath, the bigger the connections, the better they flow, but also the bigger the connections are, the more that you're going to have the pressure impacts if you're trying to connect a system under pressure, or you're going to have more forces to be able to connect it. So trying to get that trade-off worked out for couplings. The same thing goes for installation of hoses. Larger hoses have more insulation force to be able to assemble things together as you're putting together a large system. Just making sure you have those things laid out in advance is key. And again, yeah, like I said, if parts are under flow potential, or if the system's live as you're trying to connect some of these systems up, just be able to consider which parts you're using and to make sure that they're designed for that, and will give you a suitable connection force to be able to get it together. Another key is fluid compatibility. All the components and subcomponents need to be considered for this. All the hoses, fittings, couplings, O-rings, everything needs to be set up to make sure that it's compatible with the particular fluids you have. Like I said, if you got an oil system, dielectric oil for an immersion versus a glycol water system, you're going to be using different O-rings, different hoses, and you want to validate that those are compatible with the particular system that you're using. The rubber components are tailored to those particular fluids, and the significant testing is typically done on those to make sure that they are compatible. The same goes for metallic components. Galvanic corrosion is a significant consideration. Any kind of exposure to the environment that's out there is key to make sure that as you go forward, there's not going to be any corrosion concerns. The parts aren't being subjected to something that is unexpected. And in terms of, for instance, the system considerations, typically you want to design the system so you're not getting a lot of condensation on the parts. But if there's condensation, if there's certain things in different areas, you want to make sure that the parts are expected and can survive the full life cycle of the part, to make sure that you don't have that as a problem. Typically that is expedited life testing. At Parker, we'll do a lot of the HALT tests, highly accelerated life tests on any of these different components, to be able to verify that over time they're not going to end up causing problems in year 3 or 4. All of a sudden you have a lot of hose failures, or you have a lot of coupling failures. In particular, a lot of that was going to take into consideration both the temperature and the pressure and the media compatibility all together in the proper application, to make sure that everything is going to work together. So through that, all the liquid cooling can be something that can be added to a data center. It's something that, with the right choices of products, it's something that absolutely can give you an increased performance, as well as give you a lot of efficiency and savings going forward.
Well, after all these considerations, the question can be how to make the transition. And here are some examples of how some companies did it. So, the first company was using air cooling technologies and had no experience with liquid ones. They didn't have the knowledge internally to design a liquid cooling system. So they decided to use experts in this kind of applications and asked Parker engineers to support. And that's what we did. Together with the customer, Parker engineers dimensioned and designed the full distribution circuit of water glycol, in this case, linking the CDU to the cold plate. These include manifolds, quick disconnect couplings, fittings, hoses, tubings, and breathing valves. All the elements were designed, produced, and assembled by a single supplier and delivered as one part, as a kit, which additionally is 100% leak tested. The second example is a technology company that had several data centers in the United States. They were using already liquid cooling, but experienced intermittent leaks. They had difficulties to find the root cause. So they called Parker to support, and the inspection of the quick disconnect couplings determined small amounts of debris that caused leakage. The solution Parker brought is an assembly process based on clean room practices and helium leak tests on the parts. The benefits for the company are, of course, the reduction of downtime of the different parts of the data center for service because no leaks occur anymore. So the third example concerns a cloud computing company. This company designed and built their own liquid cooling system, and they installed it in different locations. They used tap water and experienced quick disconnect couplings failure and leakages due to contamination, mainly line scale built up, and corrosion. In this case, the mix of different metallic materials in presence of water was creating galvanic corrosion, and some of the components were corroded and created some contamination. The solution chosen was to build the couplings in thermoplastic, which is neutral in terms of corrosion, and it's much less sensible to line scale. The benefits are that the leakages have been suppressed, so the downtime for service reduced, but also the cost of the components have been reduced by using thermoplastic, which is cheaper than metal. Another benefit is the reduction of the lead times to get the parts, as they are locally sourced from Parker next to the customer's location. So the fourth example is about a company that is building liquid cooling installations. They plan to use dielectric fluid and two-phase direct-to-chip technology. They were struggling to find a good solution, assuring chemical compatibility and leak-free connections. Parker engineers designed and validated a two-lines connection for both the liquid and the gas circuit. This had been done using also a strong partnership with a local distributor to assure the best supply chain solution for the customer. The benefits for the company is an easy-to-handle, high-performance connection with no leaks, as well as a good service. So, to resume, Parker offers a full portfolio of products for thermal management that are proven to efficiently assure absorption and redirection of the heat away from critical parts. In addition, Parker can support you to the dimensioning of the fluid cooling system and can assure the supply of assemblies of this one. So some example of the most successful products. The LiquiFit push-in fitting, they are made in thermoplastic with stainless steel adapters. There is no need of crimping, glue, or welding to connect the tube. Just insert the tube into the fitting. The connection and the tightness are done. It's also easy to disconnect by pushing the gray button and pull the tube out of the fitting. Then the caustic is even a simpler solution, as there is no need of threaded connection to fix it, but only a hole at the right dimensions and roughness, of course. It is very compact solution and quick to install, so it saves time at installation and increase productivity. Parker's dripless quick disconnect couplings have been especially designed for thermal management liquid applications more than 20 years ago. The specific internal design assures zero spillage and no failure at disconnection, being independent of the line scale accumulation. The sizes available from 3 millimeters to 32 millimeters nominal diameters are covering the connection needs in different areas of the cooling circuit, following the flow needed, and the various metals, brass, stainless steel, aluminum, offer a compatible solution for various installations. Then the blind made version offers also various sizes and materials, as well as the same special internal design for thermal management. The advantage of this solution is to be able to connect without touching the couplings. They accept a misalignment of plus minus 1 millimeters to absorb part of the installation's tolerances. Parker proposes EPDM hoses for water cooling applications in various internal diameters in order to answer to the needs of connection in various places of the data center cooling system. They have high compatibility characteristics, ozone and abrasion resistant cover, for example, for the Parker 627 series. For this series, the peroxide cured option offers even higher thermal resistance and compatibility. Some data centers applications request a flame resistance rating, so Parker qualified some of the hoses following the UL specification. The fluoropolymer tubing outperforms all the conventional polymers and offer high thermal compatibility. It is not flammable and have outstanding ozone and UV resistance. It had the advantage also to bring no contamination in the circuit, and the corrugated models offer a very small bending radius, so they can be installed in very small spaces. Parker M&D series represents customized in-rack manifold solution designed to distribute the right amount of fluid to each individual cold plate, so the heat is uniformly removed from the processors. The dimensioning and design is made in cooperation and following the customer's installation needs. Flow simulations can support the dimensioning and the internal sections in order to assure the lowest pressure drops and the best distribution flow at all levels. The materials are chosen to assure compatibility with the other circuit elements to avoid corrosion. We also take into consideration easy access and dismounting for maintenance if necessary, in line with the customer's installation. They can be equipped with standard or blind-made Parker couplings, as well as with the needed hose assemblies flow regulators, and other elements. The complete assembly is leak tested before shipping to the customers. Today, Parker has the structure in place to support EMEA and Asia Pacific markets. Also, Parker is part of the open compute community as supplier for several parts of the cooling system. To resume all this, it is important to choose the right partner to design and supply the thermal management system. You need to consider thermal management efficiency, serviceability, solutions for the complete circuit, compatibility, but also think about a global supply for all these elements. Additional to a worldwide presence and expertise, Parker is also one source for assembly of thermal management circuits, at least in EMEA and Asia Pacific. Also, Parker is, as I said, part of the open compute community and supply several parts for this cooling system. So thank you. And now if you have any questions, we are happy to answer them.
Great. Thanks, Liana and Tim, for a great presentation. Getting to our questions here in just a moment. If you'd like to submit a question, type your question into the Ask a Question box and hit the Send button. And also, please take a moment to complete the feedback form that will appear on your screen at the end of the webinar. So we have a number of questions that have come in from various places. Let's start with this one. Are data centers considering implementing liquid cooling for their power infrastructure, such as for cooling in a UPS?
Yeah, I mean, I can talk to that. I mean, it's cooling, right? So it's the same methods would apply in terms of how we go about data center actual cooling of the IT gear. It's not something that I'm terribly aware of as a big need, but it is certainly something that you would go about using the same types of refrigerants or coolants, the same types of heat rejection loops. So I'd say all the learning that's gone into a lot of the data center cooling would still apply. Most of the focus has been on IT gear in particular, and a lot of that has to do with just because of the performance required out of each set of IT gear has been going up so dramatically, particularly with a lot of the artificial intelligence. We're going to get even more of that coming in the next few years, to where that has been really the primary focus.
Yeah, we've seen a lot of growth in AI and a lot of interesting ways that people are using AI to in ways that might not have been thought of in the first stage. So it's going to be interesting to see how a lot of this continues to develop. Let's look at another area. Do something basic. How do you keep a system from leaking?
Well, I'd say that's not exactly basic. It is the probably the key element, because that's I would say what has kept liquid cooling really kind of back for some time is the fear of leaks. You have a lot of electronics and water aren't really. It's not really a marriage is made in heaven. It's not something you really want to put close together all the time because of that potential. But that's where it goes back to the basics. It comes back to system design. All the right parts have been qualified. You have the right chemical compatibility. You have the right partner that gives you a good quality product that's been validated and set up for one of these systems. So it comes down to the blocking and tackling of getting the right parts in the right application, so that you can have the confidence in them. If you wouldn't go to Home Depot and grab a hose off the shelf and put it into your system. You have to make sure that it is set up correctly in advance.
And that leads us to this question, which is how does Parker validate the fluid compatibility for various fluids?
Yeah, I can go through that as well. I don't know if Liana, if you want to chime in as well with any of your thoughts, but fluid compatibility for a lot of our products comes down to there's a number of standard tests out in the market that will do as a general fluid compatibility, say for rubbers or for different materials. And you're always looking at at temperature and with exposure to material over time and in different stress conditions. What does it do? Does it take a set? Does it swell up and cause problems? Does it lose some of its performance? Whether it's its stiffness or its modulus, or maybe it takes a set. And so we'll tend to run through a lot of those standard material tests. And then we'll also qualify the part in application. So we'll have an actual product, and we'll set up a test stand and do some of that halt testing we talked about, some of the highly accelerated testing. And that's going to take a lot of the parameters from an application. Like I said, we kind of focus on data center cooling to make sure that we understand it very well. And understand where all the failure points are, and take it so that we know all the failures are significantly in excess of any kind of application parameters, and we can have that confidence in the materials we're choosing.
Well, let's talk about standards for just a second. Are there any standards out there to consider when looking at data center cooling components?
Well, I would say it starts to talk around. There are some beginnings of startups, but nothing is complete for the components. So it starts to be some system standards. Thinking about the open compute community who's trying to put in place some standards of cooling systems about this, but nothing is defined currently in the market.
Very good. Does Parker provide any installation or integration services?
Well, I would say not at this time, but Parker have a vast distribution network with knowledge of this industry, and of course we can supply with all the needed components and the knowledge and expertise so that they can do this.
Very good. We have time for a couple more questions. Tim touched on materials briefly. Talk about the preferred materials for coolant conveyance.
Yeah, sure. I mean, it does come down to what exactly fluid are you using in particular. There's a lot of glycols out there, and so we end up using for a water glycol system. Typically, there's an EP that an ethylene propylene type of rubber that's going to give us a good solution. Parker's got a pretty good selection of rubbers that have come out for that type of a market. If you're using an oil, however, a dielectric oil, obviously you have to stay away from that. It'll cause significant problems. So for you end up with different materials for some of those systems, whether it's a nitrile or fluorocarbon type rubber solution, as well as there is some work that needs to go into some of the immersion systems in particular. The fluid vendors tend to be concerned about not having anything leach into their system as well or contaminate the fluids, which is something else to consider.
Very good. We have time for one more here. Does Parker have a fluid coupling that provides inlet and outlet flow?
Well, currently, I would say no. If the need is to connect and to disconnect in the same time the inlet and outlet, but this is kind of multi-coupling in a big dimension, of course, to assure the right flow for inlet and outlet. And Parker have this kind of products for other applications. We have the knowledge. It's, I would say, easy to adapt the thermal management technology to develop something like this very quickly.
Yeah, and I'd say too, Liana, I think if we're talking about, we're connecting multiple lines, you're connecting the inlet and the outlet at the same time. I say that's what we do a lot of times with those blind mate couplings as well, right? As you connect a system together, you're going to blind mate multiple connections at the same time, and it's set up to be as part of the IT gear typically, or a different manifold setup depending on exactly the application. But it is something that we have offered in a lot of solutions, a lot of different applications as well.
Well, that's about all the time we've got for questions today. If we didn't get to your question during the presentation, we will be getting back to you via email. I want to thank Tim and Liana for a great presentation. On behalf of Electronic Design and Power and Motion, I'd like to thank Parker Hannifin for sponsoring today's event. And of course, thanks to all of you for joining us. Have a great rest of your day and stay safe out there.
Thank you.